We are going to learn how to evaluate limits with indeterminate forms 0 times infinity and infinity minus infinity using L'Hopital's rule. Let's first learn how to evaluate limits with the indeterminate form 0 times infinity. If you're given that the limit of f of x as x approaches a is equal to 0, and the limit of g of x as x approaches a is equal to infinity, then you get that the limit of f of x times g of x as x approaches a is equal to the indeterminate form 0 times infinity. I've written down here some steps that you can follow to evaluate this indeterminate form. What you're going to do is you are going to rewrite f of x times g of x as either f of x divided by 1 over g of x. That is going to give you the indeterminate form 0 over 0, which we know how to evaluate using L'Hopital's rule. Or you are going to rewrite it as g of x divided by 1 over f of x, and this is going to give you the indeterminate form infinity divided by infinity. And then you can use L'Hopital's rule. When you decide which way to rewrite your function, you need to make sure to choose the form that has the easiest derivatives. Down below, we are going to walk through an example, and I'll show you how to determine which way to rewrite it. Here's our example. We are going to evaluate the following limit. Our limit is the limit of sine x times natural log x as x approaches 0 from the right. X is approaching 0 from the right because the natural log is only defined when x is greater than 0. We're going to start by just substituting in that x is approaching 0. So this is sine of 0 from the right times natural log of 0 from the right. Sine of 0 is 0, and then the natural log of 0 from the right is minus infinity. So we get the indeterminate form 0 times infinity. This means that we need to rewrite our function. Let's go ahead and let's do that. We're going to write this as the limit as x approaches 0 from the right. Now we have to decide, do we want to put 1 over sine x in the denominator or 1 over natural log x? 1 over sine x, let me go ahead and write this over here. 1 over sine x is cosecant x. We know how to take that derivative. We also know how to take the derivative of 1 over natural log x, but it's a lot more complicated. So I am going to choose to put the natural log x in the numerator, and then in the denominator, I have 1 divided by sine x. Let's see what this gives us when we let x go to 0 from the right. This is natural log 0 from the right, all over 1 over sine 0 from the right, and this is minus infinity divided by 1 over 0, so we get minus infinity over infinity. And that is the indeterminate form that tells us that we can apply L'Hopital's rule. So that's what we're going to do. I'm going to put a LH over here so that we know we're using L'Hopital's rule. And this gives us the limit as x goes to 0 from the right. Now we're going to take the derivative of natural log x, which is 1 over x. And now we're going to take the derivative of our denominator. Let's just make a note here that this is cosecant x. The derivative of cosecant is minus cosecant x cotangent x. And now we need to know what that limit is. I think the form that our limit is in makes it difficult to evaluate things. So I am going to change this back to be the limit as x goes to 0 from the right of 1 over x on the top, and then I'm going to write cosecant as 1 over sine x. And then let's put in that cotangent is cosine x over sine x. And we're going to rewrite this as the limit as x goes to 0 from the right. We're going to take the minus sine squared x up on top, and then in our denominator, we have an x cosine x. And that's much easier to evaluate. It's really common when you use L'Hopital's rule to have to simplify as you go along. Let's now substitute in that x is approaching 0. Because we don't have the natural log anymore, I am just going to write down 0 instead of 0 from the right. So this is minus sine 0, all divided by 0 times cosine 0. Sine of 0 is 0, and then we have 0 times cosine of 0 is 1. So we get 0 divided by 0, and that is the other indeterminate form that tells us that we can use L'Hopital's rule. So we are going to use L'Hopital's rule again. And let's see what we get. This is the limit as x approaches 0 from the right. We're going to take the derivative of minus sine squared x. We're going to have to use the power rule. So this is minus 2 sine x times cosine x. And then in the denominator, we are going to have to use the product rule because we have one function and a second function. The derivative is our first function times the derivative of our second, and that is a minus sine x. And then we have our second function, cosine x, times the derivative of our first. The derivative of x is 1. Now let's go ahead and let x be equal to 0. So this is minus 2 sine of 0 times cosine 0, all divided by 0 times minus sine 0 plus cosine 0. Sine of 0 is 0, so this is minus 2 times 0 times 1, all divided by 0 plus 1 in our denominator, and this gives us an answer of 0 over 1, which is equal to 0. And that's our final answer. Let's now look at our other indeterminate form, infinity minus infinity. If we are given the limit of f of x as x approaches a is infinity, and the limit of g of x as x approaches a is also infinity, then the limit of f of x minus g of x as x approaches a is the indeterminate form infinity minus infinity. Let's now walk through how to evaluate this indeterminate form. What you're going to do is you are going to put infinity minus infinity into the form 0 over 0 or infinity over infinity by factoring or rationalization. That just means multiplying by a conjugate or getting a common denominator. Once you do that, your limit will be in the form 0 over 0 or infinity over infinity, and then you can use L'Hopital's rule. We are going to go over 3 examples, one for each of the techniques listed above. We're going to evaluate each limit. The first limit that we're going to evaluate is the limit of x times e to the 1 over x minus x as x goes to infinity. First thing you always want to do is substitute in what x is. So this is infinity times e to the 1 over infinity minus infinity. This is infinity. 1 over infinity is 0, so we have e to the 0 minus infinity. E to the 0 is 1, so we have infinity minus infinity. This is an indeterminate form, and we now need to put this form into 0 over 0 or infinity over infinity. Notice that with the function that we're given, let me go ahead and highlight this. Can you see that there is an x common to each term? Because of that, we can factor out an x. So let's go ahead and let's do that. This is the limit as x goes to infinity. We're going to factor out an x, and we're left with e to the 1 over x minus 1. Now we want to go ahead and substitute in that x is equal to infinity. So we have infinity times e to the 1 over infinity minus 1. This is infinity. E to the 1 over infinity is e to the 0 minus 1. So this is infinity to the 1 minus 1, which is infinity times 0. This is an indeterminate form. It's not 0 over 0 or infinity over infinity, so we have one more step to do before we can use L'Hopital's rule. What we have to do is rewrite this limit, let's highlight this, in such a way that we get 0 over 0 or infinity over infinity. So we have to take either the x or the e to the 1 over x minus 1 to the denominator. It's going to be a lot easier if we put x in the denominator. So that's what we're going to do. This is the limit as x goes to infinity. We're going to have e to the 1 over x minus 1 in the numerator. And then in the denominator, we're going to have 1 over x. Let's see what that is equal to. We're going to let x go to infinity. So this is e to the 1 over infinity minus 1, all divided by 1 over infinity. 1 over infinity is 0, so this is e to the 0 minus 1, all over 0. So we get 1 minus 1 over 0, and we get 0 over 0. Now, finally, we have a form that we can use L'Hopital's rule. I'm going to put an LH over here so we know that we are using L'Hopital's rule. And now we're going to take the derivative of the numerator and the derivative of the denominator. The derivative of e to the 1 over x minus 1 is e to the 1 over x times the derivative of 1 over x. Let me go over here and let me write down in the left-hand side the derivative of 1 over x. This is equal to minus 1 over x squared. If you haven't memorized that, that might be a good one to memorize. It just makes things go a little bit quicker if you have that memorized. So back to our problem. We had e to the 1 over x. Now we're going to have to multiply by the derivative of 1 over x, which is minus 1 over x squared. And then we have a 1 over x in the denominator, so we're going to write down that derivative, and that is minus 1 over x squared. One thing that is really nice with this problem is that the minus 1 over x squared cancel out, and so we're just left with e to the 1 over x. This is the limit as x goes to infinity, e to the 1 over x. Now we let x go to infinity, so this is e to the 1 over infinity, which is e to the 0, and this is equal to 1, so the value of our limit is equal to 1. Let's now look at our second example. This is the limit of the square root of x squared plus x minus x as x goes to infinity. We're going to start by letting x go to infinity, and this gives us the square root of infinity squared plus infinity minus infinity. So this is the form infinity minus infinity. That is an indeterminate form, and we can evaluate this indeterminate form by either factoring, by rationalization, or by getting a common denominator. Notice that this problem has a square root, so we are going to use rationalization, which just means we're going to multiply by a conjugate. Let me write down here that the conjugate of the square root of a minus b is the square root of a plus b. Let's now use that. We're going to write this as the limit as x goes to infinity. We have the square root of x squared plus x minus x. Now we are going to multiply that by the conjugate. So we have the square root of x squared plus x. And we can't change the problem. So whenever we multiply by the conjugate, we also have to divide by the conjugate. X squared plus x plus x. Now we have to multiply this out. We are going to use the FOIL method, FOIL. That is the first, outer, inner, and last. So we have the limit as x goes to infinity. We are going to multiply the first terms. Both of those are the same term, and they have a square root. So we get x squared plus x. Now we're going to multiply the outer terms. So we get an x times the square root of x squared plus x. Now we're going to multiply the inner terms. So this is a minus x square root x squared plus x. That's nice. Those terms are going to cancel. And then we're going to multiply our last terms, which is minus x squared. And then all of this is divided by the square root x squared plus x plus x. Now let's look and let's see what cancels. Our x squared terms cancel, and then our square root terms cancel. So this is really nice. We end up with the limit as x goes to infinity of x all divided by the square root x squared plus x plus x. Now let's go ahead and let's let x equal infinity. So we have infinity all divided by the square root of infinity squared plus infinity plus infinity. So this is infinity divided by infinity. That is an indeterminate form. Now we can go ahead and use L'Hopital's rule. This gives us the limit as x goes to infinity. The derivative of x is 1. Now we have to take the derivative of this term right here. That derivative is a little bit complicated. I think it's easier if we write down over here on the right the derivative of the square root of u. This is equal to du dx all divided by 2 times the square root of u. Let's now apply that. Our derivative is the derivative of what is inside, so that is 2x plus 1. And we're going to divide that by 2 times our square root. X squared plus x plus the derivative of x, which is 1. Now we need to let x go to infinity, but before we do that, I am going to simplify this term right here and divide both the numerator and the denominator by x. This gives us the limit as x goes to infinity, 1 all divided by 2 plus 1 over x, all divided by 2 times the square root. Now, when we divide by x inside the square root, we have to divide by x squared. So this is 1 plus 1 over x, and then we have our plus 1 on the end. Now we're going to let x go to infinity, and we get 1 all divided by 2 plus 1 over infinity, all divided by 2 times the square root of 1 plus 1 over infinity, plus 1. And this is 1 all divided by 2. 1 over infinity is 0, so we just get 2 divided by 2 times the square root of 1 plus 1. And this is 1 divided by 1 plus 1, which is equal to 1/2. That was a long problem, but we did it. Our limit is equal to 1/2. Let's now look at our third example. In this example, we're taking the limit of 1 divided by natural log x minus 1 over x minus 1. Let's start by letting x be equal to 1. So we have 1 divided by natural log 1 minus 1 over 1 minus 1. Natural log of 1 is 0, so this is 1 over 0 minus 1 over 0. And we have the indeterminate form infinity minus infinity. To evaluate this, we need to notice that in our original function, we have one term minus another term. And when that happens, it's usually good to get a common denominator. So let's go ahead and let's do that. This is the limit as x goes to 1. Our common denominator is going to be natural log x times x minus 1. And then up top, we're going to get x minus 1 minus natural log x. Now, let's evaluate this again and let x be equal to 1. This gives us 1 minus the natural log of 1, which is 0. And then in the denominator, we have the natural log of 1, which is 0, times 1 minus 1. And we get the indeterminate form 0 divided by 0. This indeterminate form can be evaluated using L'Hopital's rule. So let's go ahead and let's do that. Let's put our LH here so we know we're using L'Hopital's rule. Now we're going to take some derivatives. We're going to start by taking the derivative of the numerator. That is equal to 1 minus 0 minus the derivative of natural log x, which is 1 over x. And now we're going to take the derivative of the denominator. Notice in the denominator we have two terms. Here's our first term, and here's our second term. So we are going to need to use the product rule. We have our first term, natural log x, times the derivative of our second, which is 1, plus our second term, x minus 1, times the derivative of the first term, which is 1 over x. Now, before we go ahead and substitute in that x is 1, let's make this easier by multiplying both the top and the bottom by x. That's just going to get rid of that 1 over x term. This gives us the limit as x goes to 1. We have x minus 1 in the numerator, and then in the denominator, we have x ln x plus x minus 1. Now let's go ahead and let's let x be equal to 1. So we have 1 minus 1 in the numerator, and in the denominator we have 1 times the natural log of 1, which is 0, plus 1 minus 1. And this gives us 0 divided by 0 again. Hang with me, I know these are long problems. This is our indeterminate form, but the good news is we can keep using L'Hopital's rule. So let's go ahead and let's take the derivatives again. We have the limit, x goes to 1. The derivative of x minus 1 is 1. And then in our denominator, we again need to use the product rule. Here's our first term, and there's our second term. So we have the first times the derivative of the second, which is 1 over x, plus ln x times the derivative of x is 1, plus the derivative of x, which is 1. Let's go ahead and let's rewrite this and clean up a little bit of the algebra. We have a 1 on the top, and in the denominator we have, we have a 1 here and a 1 here, so this is 2 plus ln x. Now we can go ahead and let x be equal to 1, and this gives us 1 divided by 2 plus the natural log of 1, which is 0, and we get an answer of 1/2. And that's what our limit is equal to.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.